Exam question revision video for GCSE circle theorems. So we'll have a look at the question. We've got a circle with various lines inside making shapes. So what's our thinking here? We can see what we've got to find, that angle x. The first thing to notice is that the diagram is not drawn to scale, and it says so, and that tells us we can't just measure the angles with a protractor. Okay, so we've got triangles and we have a circle, so it could be trigonometry, could be circle theorems. The angles in a triangle add up to 180 degrees, and this will probably come into it. In fact, if we look at the triangle ADC or ACD, we know the angle at C and we want to find out the angle at A. So if we knew the angle at D, we could use the sum of the angles in a triangle being 180 to find out what x is. Okay, so the only other information we do have is we know the angle at B. And can we use this to find out the angle at D? And in fact we can. And what we use is a theorem concerning cyclic quadrilaterals. That means a four-sided shape where all the corners are on a circle, and the opposite angles in a cyclic quadrilateral always add up to 180 degrees. So for example, in this one we've got A plus B, they're opposite to each other, and C plus D are opposite to each other, so A plus B is the same as C plus D and they equal 180. So using that, we have that because we've got a cyclic quadrilateral here going A, B, C, D, then the angle at D, ADC, plus the angle at B, ABC, they must add up to 180. That means that ADC is 180 take away ABC, which is the same as saying 180 take away 71 degrees. And if we do that sum, we get 109. So we now know what ADC is, and we can then use the I popped it on the diagram there, so there it is in our triangle ADC, and we can now say that x is 180 take away the other two angles, so that's the 26 plus 109. That's the same as 180 take away 135, which gives us 45 degrees. Okay, now we'll have a look at an alternative question. So this is using different circle theorems, or maybe the same. Let's see what happens. So we're asked first of all to find the angle DBC, and what we may be able to see straight away, but we might need to do what it says on the screen. If we isolate what we need to find DBC, we can see that we need to use the alternate segment theorem. And if we put the lines on, you can see that triangle CDB, and then the other red line which could extend to P and to T, so the line PT is a tangent. And the alternate segment theorem tells us that in this situation the angle made by the tangent line with the line CD, so that's the angle PCD, is the same as the angle DBC in the triangle. So straight away we can say that DBC is equal to 56 degrees. So that's basically knowing the alternate segment theorem and being able to apply it. Finding BOD is a bit trickier, and it requires two steps using two different circle theorems. So first of all, we use the one we've used before, opposite angles in a cyclic quadrilateral theorem, and this tells us that BCD plus BAD must be 180 because ABCD is a cyclic quadrilateral and those two angles are opposite to each other. So that means we have BCD is 180 take away BAD, that means it's 180 take away 112, and that gives us 68 degrees. So we now know what BCD is, and the second circle theorem we need to use is that the angle subtended from a chord, in this case BD, to the centre is double the angle subtended to the circumference. So we have a chord DB, so that's why D and B is circled, And if we draw from there down to the circumference at C and back to, so down from B and back up to D, the angle formed there is half of the angle formed if we go from B to the centre of the circle and then on to D. So, because we know what the angle at C is, we can use this, and it tells us that BOD, which is the one we've been asked to find, is 2 times BCD. That means BOD is 2 times 68, which we've just worked out before, and that means BOD is 136 degrees. Okay, the bonus material in this video is a proof. So how do we know that the opposite angles in a cyclic quadrilateral always add up to 180 degrees? Now, we can't draw all possible quadrilaterals in all possible circles, as that would take an infinite amount of time, and we don't have an infinite amount of time. And this is why proof is so important in mathematics. And we need a proof. So in the diagram, we have a cyclic quadrilateral, ABCD, and what we've added in is radii from the centre to each of the points. So all those 4 black lines going from O to A to B to C to D are radii and therefore the same length. And that means that the triangles that are formed, so OAB and OBC and so on, must be isosceles because each of them has 2 of their sides as radii and all the radii are the same length. And therefore, in an isosceles triangle, the angles at the foot of the 2 sides that are equal must be the same. So I've marked them on as alpha in the triangle OAB, and we can go round for all the other triangles. So for OBC we've got beta, for OCD we've got gamma, and for ODA we have delta. Now, that means we can deduce that because the angles in a quadrilateral add up to 360, then if we take the angle at B, which is alpha plus beta, and then add on the angle at C, which is beta plus gamma, and so on, so gamma plus delta, delta plus alpha, they must add up to 360. And if we look at those brackets are there to show that we're looking at the angles at each corner, but in fact we can ignore the brackets because it's all plussing, and we've got 2 alphas, 2 betas, 2 gammas and 2 deltas, so they must add up to 360. And if we half both sides, divide both sides by 2, we end up with alpha plus beta plus gamma plus delta is equal to half of 360, which is 180. Now, the angle at A is alpha plus delta, and the angle at C, which is opposite, is beta plus gamma. So you can see them underlined and marked on the diagram. And if we rearrange that, we have alpha plus beta plus gamma plus delta. So that means our alpha plus delta plus beta plus gamma must be equal to 180. And therefore we've proven that the opposite angles in a cyclic quadrilateral always add up to 180. And the reason it's always is that we could move any of those points A, B, C and D around wherever we want, and it wouldn't change the argument. So that is an actual proof.